This is a rare honor. I get to introduce Dr. Jackson. He's been very active in relativistic astrophysics. In fact, the whole spectrum of space exploration. He actually got his PhD in relativistic astrophysics, as I mentioned, from UT Austin. And then at Johnson Space Flight Center, he performed, and listen to this, he performed flight crew training and mission planning, software development, orbital debris monitoring, and engineering simulation. And that is not even mentioning what he's been doing in planetary physics, astrodynamics of interplanetary dust, and Earth orbital debris, as well as interstellar flight. So he's a remarkable man and a great contributor. So Al, if you're, when you're ready, we'll begin here.
Well, I'm actually not part of Starshot, but this is motivated by Starshot. This is a little bit of a bare bones presentation, but it occurred to me that it would be interesting to know what's happening when you got to the target after being launched from the solar system, and actually to what degree of accuracy did you have to aim at the at Alpha Centauri? So so here was the objectives. You have as you saw this morning, a laser-pushed small ship from near-Earth orbit. And I'm going to take just the canonical case of it being 20%, because that takes it 20 years. Not going to do any other velocities, and especially since everybody's using 20% the speed of light. And you aim at Alpha Centauri, and even though the nominal target is Proxima, and then propagate the ship trajectory under perturbing forces, and I considered those the potential of the galaxy, and that would be the nucleus, usually called the bulge, and the disk and the halo, and also the gravitational fields of the Earth and of actually just Alpha Centauri A. And then we're going to put in errors in the boost process, and also I put the boost cutoff distance on there, but really the only thing you have to look at is the cutoff velocity, or the time that you accelerate. So here's the initial conditions are that you boost. And I included the possibility of using lasers or microwaves. The details of the boost are taken to be completely ideal. That is, that you successfully boost the spacecraft up to 20% the speed of light. And it's actually the details in that boosting process, which was talked about this morning, which gives you the final transfer state, our initial transfer state. So I'm just taking the state vector as it results right at the end of a boost. And that will actually have some consequences for the 6 degree of motion trajectory before it cuts off. And so I'm only taking the errors and the pointing, initial distance, and velocity. And it's interesting that the simple picture of the boost is that it only takes like 258 seconds at, by the way, that's at like 10 to the 4th Gs. And you're cutting off, I put 1,200 Earth radii, but it's really 20 lunar distances. Let me go here now. The interesting thing is you're aiming at the Alpha Centauri system. Actually, you're aiming at a ellipsoid, because from the coordinate system, and I'm taking the coordinate system to be Earth equatorial inertial in the year 2000. So this is a standard system. If you're from the Hipparchus data, if you just looked in the sky, you would be able to easily find it. But in terms of rectangular coordinates at the target, we don't know the position in that coordinate system to better than like about, I think it's 10 AU in the Z direction and roughly about 400 in the X and Y. Not very big distances compared to 4 light years, but it is an initial dispersion and error, and you're aiming at that. I took as a success criteria that you don't miss the thing more than 1,000 AU. And actually that turns out to be something I don't guess we know yet, is what are the sensitivities of the instruments, what instrumentation will you have on board for what measurements you have, and over what distance can you look at the target? I mean, how far away can you miss it? And I'm saying you can't miss it more than 1,000 AU right now. So the sun's here, and roughly about 4 light years away, going straight down in that coordinate system is Alpha Centauri. What I did is I actually took and integrated the equations of motion. There's the regular forces due to the point mass as well, the sun and Alpha Centauri, and then the only other gravitational forces are, the gradient of this potential, and the potential is roughly, is this. This is the disk, or this is the bulge, or the nucleus. These are well-known fitting potentials for being able to describe stellar motion in the galaxy. And then the disk and the halo have a similar potential. That RG is the distance of the object from the center of the galaxy. This is in galactic coordinates, and the A and the Z is these have to be transformed into the equatorial system, but that's galactic Z, and then the B's and the A's are actually scaling factors that take account of the size of the galaxy, and the bulge, the disk, and the halo all have different masses, and they also have uncertainties attached to them. I tell you what happens when you calculate these forces, even this one, are so small that that's essentially a rectilinear trajectory. You could just use an analytic solution to solve this problem. I kept a numerical integration in there because I kept hoping to find some kind of forces that would change it. Well, integrated with this is actually with a 15th order RK, implicit RK. That's the actual trajectory, that you get. Sun to, Centauri system. You know, when you start out, you go by Neptune's orbit in 19 hours, Pluto in a day, the heliopause in 2 days, and it's interesting, to reach the Oort cloud boundary takes 8 years, but that's at 100,000 AU or more. So then the crux of the problem here is mainly in these quantities, mainly in the pointing angles. And if you make the flight path angle and the azimuth angle 0, then you're just essentially putting errors into the right ascension and the declination at cutoff. Now this is right at cutoff. So I spread them between as much, well, the minimum spread was a 100th of a degree. I loosened that up, and what I did is I picked the variation in these out of normal distribution. So each one of them is distributed normally, and the other parameter is the boost time, and did that about the same. This is the raw result at the end of 20 years in the propagation. If you fix the propagation time and you fix the velocity to be 20% the speed of light, you wind up pretty much with a kind of a sheet of, well, I'm sorry, I should say there's 1,000 trajectories that I put in. So that's 1,000 spacecraft launched all at, well, they weren't all at once, but, and so that's schematically what it looks like. It doesn't tell you a lot, except that they're spread. This is the differences in the location of the Centauri system after 20 years versus where the spacecraft is. Not to scale is the Centauri error ellipsoid. And you've got this, because you're only taking kind of a square dispersion in the launch angles, you get a thing that looks like that. Now, it's not too bad. You can see if the deviation is only a 100th of a degree, these are the dispersions in the various axes. That's, well, up at the top you can see that the mean is about 330 AU. A better way to look at it would be a histogram. So with 100th of a degree, you can hit, well, you can hit a mean of 45. I think that other one was I think it was like 1/10 of a degree on the other one. So if you can control the errors in the launch angles to 100th of a degree, then the miss distances are very reasonable. If you put that up to 1/10 of a degree, it's still not too bad. Your mean is only like 337 AU, and with a standard deviation of 128. If you relax that further to 1 degree, then your mean goes up to like 3,400 AU, and a standard deviation that's like that. So now, what that tells me is that you really need to control the final state directions to within a thousandth of a degree if you really want to hit the target. So the arrival state in terms of missed distance is almost solely dependent on the initial orientation, on those two angles. That makes the precision of the injection state important. Therefore, the stability of the launch problem is important, and that's where everything comes in. You're going to have to hit the thing, just with that exact, within those number of degrees. The whole problem may be a little bit more complicated than this, but I'm just doing this as a first cut. If there's a requirement that a ray or a subset of the ships all arrive in, say, a volume that's where they have to be communicating with one another, or they're used as some kind of observational process, then the cutoff velocity becomes important. I didn't put that up here, but there's a spread in that sheet. And so that one has to be kept down to about almost 1,000th of the 20% the speed of light. So that one's very sensitive. There's also if the spacecraft got charged, it could be perturbed by the galactic magnetic field. But there's a paper by Hong and Loeb recently that showed that was only like 0.2 of an AU at target. Other perturbations are possibly in there, but already you're going, it's like a rifle shot from the solar system to Alpha Centauri, and the only thing that seems to be a factor is how well you do your launch vector. There are still some uncertainties in how good the inertial system is, and that can be improved. Well, that's all I have for right now.
Is the galactic magnetic field strong enough to provide potential in-course corrections?
No, it's not. It's really weak. Unless you get the thing charged up to some impossible state.
So now that I understand what you did better, you did account for the errors in our knowledge of the distance and motion of Proxima Centauri itself?
No, that's why I put up an error ellipsoid, and it's probably like a little worse than that. So I actually don't know all of the uncertainties in the errors in the coordinate system. Like I said, I use Hipparchus data, and I think that's IERS.
I looked up some of the work that I was working on, and the errors are not much better from ground-based observations, but Gaia should improve it. But it's only going to be by like a factor of 3 or maybe 10. But I'm more than happy to work with you if you want to update those numbers. Cool.
You showed, I think, a snapshot in time after exactly 20 years. That formed a sheet. What does it look like if you plot the point of closest approach? Does it have a different shape, or what do you learn by doing that?
Well, I mean, the closest approaches are inside that sheet. Wherever, there'll be some that are farther away, and then if you look at the histogram, you'll see that there's a certain percentage of them that come close by, within 100 AU.
Where did the 1,000 AU number come from? Because a 1 gram camera, you're going to have to get to like within 1/10 of an AU to see anything.
Well, that's what, yeah, the guys are going to have to tell me what kind of instrument they're going to put on there to how far away they can see the target when you get there. And I don't know.
Is there any non-negligible effect from for random motion added due to interaction with dust within the solar system?
Well, not that I could tell. The drag is, once you get up to 20% the speed of light, you really have to, you've got to expend, for instance, to stop the thing at Alpha Centauri, you would have to do 4 Saturn V burns to stop it.